Yes, so good afternoon or good morning from the time you'll be watching. My name is Ogenrwoth and I'm going to be giving just a short summary of what I've been able to pick throughout this course, that is Diploma in Machine Learning with Python. So just in brief, I was able to learn a lot from the practical implementations of the various machine learning algorithms that we already use, and then also some of the different perception of looking at things, particularly maybe just to give in brief. For example, looking at problem solving as coming up with rules. So that was able to really expand my view in the field of machine learning and then also problem solving generally. So without further ado, let me begin my presentation. So first I wanted to begin by problem solving, since machine learning is basically problem solving. So I wanted to look at the traditional way in which we are solving problems, and if you can see from this picture or this illustration as an example, as humans or with traditional computer programming, what we would do is study a given problem that's given to us, then we would come up with a set of rules about that problem that would lead us to the solutions, and then we would evaluate that particular solution. So if the solution is correct, then we would deploy or iterate or improve the solution. And then if there is any error, we would analyze the error, then we would repeat the whole process again. So this approach works or has been working for us, but especially when we had little data. So say for example, when we are converting degrees Celsius to degrees Fahrenheit, there is just a fixed set of rules. So we would just say, for example, degrees Celsius, Fahrenheit is equal to 5 out of 9 times the temperature in degrees Celsius, then minus 5. I'm not so sure, but that is the formula that was also discovered by maybe a group of scientists who did a couple of experiments to come up with these rules. So you find that such a problem is simple and doesn't require machine learning per se. So if you look at machine learning or why we need it, machine learning is basically an automatic way of coming up with these rules. So let us take, for example, recently the large language models, where the rules are so many. I'll just give an example of maybe GPT. How it would work is that it keeps guessing the next token. So if you look at, if I say for example traditional, for machine learning to get the next word, the rules are so many, because if you look, we have I think about 32,000 words that are registered, maybe in English only. So coming up with a rule that can very well specify that problem is very hard, or it's hard to come up with traditional programming or just basically with our minds. Our brains are able to do it, but yeah, so our brain is kind of a complicated or a complex system. It can be able to do that, but over some period of time. So we started learning how to talk from childhood until now. So that is basically problem solving traditionally. Then if we look at the next slide, I'm going to talk about machine learning. And basically machine learning is a field of study that enables computers to learn patterns from data without explicitly being programmed. So this is just similar to what I was talking about. And then here I talk about an example where I compare it. So the traditional approach, like I've been saying, would work on problems which have a small set of rules, and if we now have so many rules, that's where we would have to use machine learning. So we need the speed, power, and accuracy of a computer to capture all those rules. So that is just basically machine learning. So we want computers to be able to learn rules, all these patterns, without us telling them what the patterns are. So basically there are two types of learning, let's say, when it comes to capturing these rules. The first one is supervised learning. So with supervised learning, we define a set of features and their target. So a target is basically like a category or where we say if it is these features, then it has to be this target. So that would be, just in simple words, it would be we label the data, we label each data point. Say if the temperature, for example, is this, then the output is that. So that would be supervised learning. There are of course various algorithms that do that. So we have regressions that they basically work with numbers. Then we have classifications where we are classifying that this is this category, this is this category, based on the feature. Then the next type is unsupervised learning. So with unsupervised learning, we just get an agent. An agent is, in this case, the entity that's going to learn these rules, and we put it in an environment where we have all our unlabeled data, and then we make it determine the rules. So for example, we would have like clustering, the dimensionality reduction with PCA. Those are just the main examples that I was able to pick. Of course, there are various other examples in the world out there as well. Yeah, so that is basically about machine learning and the two types. Recently, there is also a bit of reinforcement learning that's coming up as a new type of machine learning. So yeah, that's just in what is in development right now. So let me go to the next slide. This is still just basically talking about the differences between supervised and unsupervised learning. I think I've already talked about it in the previous slide. I'll go to the next one. Our first example, which is KNN. So KNN, in this particular case, we used it for classification. So if you see from the definition, KNN is a non-parametric machine learning algorithm. So with non-parametric is we don't know the exact form that that particular solution would take. So what we do is we put the agent in amongst the data, and then as the data grows, also the rules grow. So yeah, so the solution is based on the size of the data. So if you look at a simple problem, a parametric problem would be, I will talk about regressions, linear regressions, where we are just finding the line of best fit. So we all know, for example, the formula of getting that. That is a deterministic problem where we have, it's a probabilistic model where we have the deterministic part and the non-deterministic part. So the non-deterministic part would be, for example, the set of features that we already have, and then the target would be our deterministic part, which is basically what we are looking to find. So we know that all that has to fit into the formula of a line. But yeah, the formula for linear regression is altered a bit so that we can cater for the various features that we have. So that is just a simple explanation into non-parametric algorithms. So I added a small illustration down here where I basically just go through key nearest neighbors and how it would work. So for example, what we would do is we get a particular data point. Let's say the data point we want to predict, then we would plot it on a graph. Then we calculate its distance to all the nearest neighbors. So for example, let's say we are going to compare it to the first three neighbors. That means we would consider the data points that are plotted here. So if this is a data point, we plotted the features and it has a particular target. So in this case, it would be, for example, a circle. Then here also it will be a circle and here a circle. So if k is equal to 3, and this is the plot of our data point that we're predicting currently, then most likely, or the machine learning in this case, would predict this circle, this to be a circle. Then if we have k is equal to 8, that means we are considering quite 8 nearest neighbors. So you would find that also the number of stars probably might exceed the number of circles. That means now we guess it to be a star, for example. So let's say if we had a k that took in all this, that means this would probably be a star because of the nearest neighbors, most of them being stars. Next, we just talk about some applications of KNN. We look at text mining, agriculture, finance, cargo, competitions. So these are just competitions where we are veiled with certain problems, then we have to find solutions to them. And if our accuracy reaches certain levels, then we can be ranked based on the accuracy of our results. So just briefly, we in this course particularly, we also implemented KNN, and just to show you the implementation of KNN. So we implemented KNN. This was regression. Okay, just let it refresh. So we implemented KNN from scratch, and as you can see, we're able to run it, and our implementation performed actually just the same with the sklearn original model that comes implemented in sklearn. So if you look at our score, just trying to find the model. So yeah, this is basically this. So what we would do is we first get the distances. So that means the distance from one data point to another. What we do, we plot all those points, and we calculate the distances. So if you can see, that's what we do here, for example. So we get all the distances, then we select k neighbors based on the distance. So in this case, we could use counter, and then we sort the values, the nearest neighbors first. We would sort the values based on their distance, and then we select n, let's say k number of neighbors. Then from the neighbors, we would go into voting, where we get the class with the most number of features within that neighborhood. Then that would be our most likely prediction for that given data point or test point. So doing this, we're able to reach the score, like I'm saying. We're able to reach 0.96, and also sklearn standard implementation also was the same value. So that means our algorithms work basically just the same. Probably maybe the time it takes, I don't know, and we haven't really tested on that. So that's just basically KNN. So back to the slides. If you look at the different pros and cons of KNN, let me start with the cons. So KNN is just simple to understand from how I've been able to describe it, and then we don't have to make assumptions about the data distributions. So that it's correct. We don't predict. So just know if there are more x, then it has to be x. Then KNN is also able to work for both classification and regression. Then it handles multi-class datasets well. So if you look at the example we use the iris dataset, which is a multi-class dataset. So then next, if we also look at the cons, there are various cons. Actually, the cons are more than the pros. So if you look at the cons, we have a slow dataset. It's slow with large datasets. The performance drops with proper scaling. Then without proper scaling. So let's say, for example, we had one feature that is large, like let's say the height of petal is so large, and then the width is so small, So that means height would how can I say it? That means height would dominate the predictions. Then prediction step is computationally expensive, calculating the distances, the neighbors, and so on. So that would also be about the speed, like I said. Then it is sensitive to class imbalance, so like I'm saying about the height. Then it can't handle any missing value. So during our EDA, we have to make sure we don't have any missing value. For our case, at least, we have the iris dataset, which is balanced and has no missing values, basically. Then next we go into decision trees. So a decision tree is a non-parametric supervised learning. That means the accuracy will grow with the data So our knowledge of the problem grows with the size of the data. Then it's used for classification and regression, and we basically just keep splitting branches into feature values to make predictions. So we would we'll use information gains and entropies to determine which feature will have is best to split on and will have less impurity at that particular step. So let's say, for example, let me just open and I use an example of ETA we did. This example, let's throw ETA. Okay, good. So for decision trees, what we would be able to do is, if we look at here, we see, for example, this normalized. So okay, let me use a normalized example. So that means if we are splitting based on sepal length and sepal width, if we look at this particular example, we know that, okay, the color codes are different. So 00 would be setosa. So we know that, this one, this feature sepal length, basically it's good at distinguishing setosa, for example. So let me just add here. So new df dot replace target, call the feature target, then the values to replace. I think I defined the list here, so it's going to be di. So do this. Okay, it's running. Okay, yeah. So so here we know that we can easily distinguish setosa from the other different iris types. Then if we look at other example, okay, so mainly setosa is kind of distinguished, so that means we don't have to go deep into the decision trees to determine them, but basically that's just what we do. We keep splitting at the best value. So if you look at here, there's less noise for setosa, and then we go into here, we still expand, there are less noise, like that. We do that until we can easily distinguish. So this is an example. This is an example of a clear category or clear class without so much noise. So this one, so petal length is going to easily separate setosa from the other iris that we have. So that's basically decision trees. Then we look into the application of decision trees. We use it, for example, in finance for credit risk. We use it healthcare for diagnosis support, and then marketing for customer segmentation. Then also fraud detection systems, phishing, and other phishing engineering tasks. So you would also see that we use it, for example, in random forest to make the decisions. We use it to train it on the bootstrap data sets, and then we can make decisions using the decision trees because of how good it is. So the pros and cons. So first of all, the trees are easy to interpret and visualize. There's no assumptions of the data. It captures nonlinear relationships well, require little data pre-processing, and all the rest. Then if you look at the cons, it's prone to overfitting and is sensitive to noise. So if there is a lot of noise, we could make the model, go into a direction of a particular category, and that would not be nice, or would impact the accuracy of the algorithm in the long run. Next, we have ensemble learning. So just I'm going to try to increase my speed a bit. Ensemble learning is where we combine weaker models to get an accurate strong model. So we use weaker models that are actually good at just prediction in a case where, for example, it would say, let's say we are predicting from 0 to 0.5 and 0.5 to 1. So if it's 0 to 0.5, we know it's a particular class. So a weaker model would be able to tell you that a particular feature is between 0 to 0.5, but will not be able to tell you directly what it is. So ensemble learning is where we use those models and then we average the results, or we count the one with the most predictions to be the outcome of that prediction. So that's basically it. Then random forest is an ensemble method. It's based on bagging. Multiple decision trees are built based on bootstrap sampling. So bootstrapping is we just separate the data set into various small features within. Then we pick and replace so that we have some sort of an unbiased models down that we can use to make these predictions. Yeah, it also goes ahead to talk about averaging and majority voting. Applications, it's used in finance for risk assessment, healthcare, customer segmentation, large-scale data problem, and so forth, and so on and so forth. Then, the applications are here. Then the pros and cons. So we see that it's robust to outliers, and so it can be able to detect outliers well based on the combination of the multiple weaker models. Then it handles nonlinear data well and reduces overfitting. The cons is that it's less interpretable than a single tree. It can be slow to train because of the multiple decision trees that is under that random forest, for example. Then it's not ideal for sparse linear data. So yeah, you can see the cons are many, as you can see here. Then next we go into SVM. SVM is let me just read. SVM is a supervised learning model for classification and regression. They find the optimal hyperplane that separates classes by maximizing the margins. So unfortunately, I wasn't able to put an illustration here. But what we'll do, we'll separate the features and then we try to separate the margins to be able to understand the nature of the problem and use it for predictions. So SVM can handle outliers and use kernel functions to detect nonlinear patterns. So that's just one of the features of it. So we use gamma parameter to control the influence of certain data points. If it's a low gamma, we know it's their smooth boundaries. Then if it's a high gamma, we know they are tight, potentially overfitted boundaries. So that's for high gamma. So applications of SVM, we use them in text classifications. Like I talked about the margins, we just expand on the margins to be able to know the difference. We use it in image recognitions where the margins are tight, bioinformatics, handwriting recognition, and so on. Then it has its pros and cons as well. As you can see here, it works well with high dimensional spaces, and also some set of cons. Then we go into PCA, which is mainly used in compression, lossless compression. So we see that PCA, which is a principal component analysis, is a technique used to reduce the dimensionality of data while preserving as much important information as possible. We want to reduce the data, but we don't want to lose information. So that's what we are aiming for, a lossless compression of data. So here you can see PCA transforms correlated variables into smaller set of uncorrelated principal components, which are linear combinations of the original features. Then we assume a linear relationship. So much similar to linear regression and SVM, where we are drawing a line, then we see the distance in between. Yes, so the application, like I said, is used in image process compression. It is in pre-processing for machine learning. We don't want our images to be large, but also we don't want it to lose key information. It's used in facial recognition, and also it's used in data visualization. It also has its pros and cons. So PCA reduces dimensionality. It assumes linear relationship as its con. So I'm not able to go through all its cons, all its pros and cons for now due to the time constraints. But basically that's just it. So just a brief summary on machine learning, or what I've been able to pick from machine learning basically. So the general concepts within machine learning that I can that I was able to learn quite clearly, that we never tune hyperparameters or parameters on test data. So we don't want our algorithms to know what our test data is, because in that way it will just train on the test data and wouldn't do any prediction. Then we have to normalize features because scales differ, and then if we have like the iris data set where we don't want the height to dominate the width, because height values are usually higher, much higher than the width values, so that means we have to normalize. So we use scaling. I think I made some plots which I'm going to show. Then we also have overfitting, where we memorize certain patterns in data, so we don't want that. Then underfitting is where the model is just too weak, it can't stand on a particular decision. Then just also a short summary, the ultimate goal or the ultimate method that can be used for every machine learning, let's say, solution to certain problems would be, first we define models, then we define the model that we want to do, we define the objectives, which should be, for example, the cost function. The cost function is just basically to help us evaluate, are we heading in the right direction or not. For example, root mean squared error, error errors, error squared errors, and so forth. They are different for different algorithms. Then we have to optimize our parameters, things like fish engineering, scaling, doing the correct EDA. Then we have to evaluate our models on unseen data, which is just test. So we have things like model selection that gives us a set of functions to help us prepare data, like a train test split to separate data for testing and for testing and for training. Then we improve. So yeah, I think that is it. And then the summary of what I've been able to learn. Thank you so much for giving us this opportunity. It was really an eye-opener, and we are looking forward to this course. Thank you.